right? So this is what we have observed so far. And that's when our A is positive. When A is negative, do you remember what we observe? Okay, let's make another figure to show when A is negative. When A is negative, and if I continue to run this second order derivative, we get pretty much the same behavior, right? Okay, except for, of course, the directions are flipped. There's no surprise because everything is symmetric for the central difference, right? We are looking equally towards the left and towards the right. So when we switch the direction of the wave propagation, we expect that the solution is just flipped over. And we do see that, right? Here we see the larger oscillation comes when the solution goes from high to low. Here, if we reverse the direction, right, when the solution goes from high to low, there is the same magnitude of oscillation here. All right. So by this logic, the two first order schemes are working also in the opposite way. We expect that if we now use the unstable scheme in the previous case, we should actually get a working solution, right? Let's try that. Move to figure 2, hold on, and we run it. And that is the case, right? We are running our first option, which gives us nines in the previous case, and now it gives us a solution. And finally, if we use the previously stable method to discretize the derivative, and we run it, and we get unstable values, right? Okay, so this is the behavior we observed. And does anybody has any suggestions of how to go about explaining what we see here? We have now a partial differential equation discretized using different ways. How do we try to assess which way is stable, which way is unstable? Any suggestions? Come on. Remember, we have a PDE, right? We discretize it into a coupled ODE. So basically, assessing which method is stable or not is basically assessing which resulting ODE is stable or not, right? And how do we assess if an ODE is stable or unstable? Eigenvalues, right? And not only, if you notice, not only we actually get a set of ODEs, we actually get a set of linear ODEs. How can you tell? How can you tell if after the discretization an ODE is linear or not? Yeah? An idea? What does linear mean to you?
Nothing is dependent on like u squared, like if everything's of u, like the first power.
Yeah, so first of all, there is no u squared, and none of the nonlinear operators we are familiar with, none of the nonlinear functions we are familiar with actually appears here, right? So that's a hint. And the real final justification for being linear or not is actually through the definition of linearness. So something is called linear when if you multiply the let's say I have something, right, an operation here, an approximate derivative. It has inputs, it has outputs. The inputs here are a vector of u's at every grid point. The output is a vector of approximate derivatives also at every grid point, right? So basically I have this input I have the input being u1, u2, etc. up to un. Let's say I have n grid points. And I have an output. That is my approximate derivatives, right? So let's just select option 1 for now. If we just selection option 1 for now, we have u2 minus u1 divided by delta x, and u3 minus u2 divided by delta x, etc. Up to the very end, the second last value would be un minus 1 divided by delta x, and the very last value would be u1 because we have periodic boundary condition wraps over minus un divided by delta x, right? So this is my input and output. And how do you tell if this relationship is linear or not? Two criterions. Both of them are very simple to check. The first criterion is if you just scale everything here by a factor of, let's say, 2, double every number here. Is the output doubled exactly or not?